All right. Well, it's 7 o'clock, and looks like there's even maybe a couple people on. So, welcome to the office hours for Big Bang to Humankind at Tufts. And if you are on, well, it looks like someone just went away. If you're on and want to ask a question, please let me know. I'll also be, monitoring my email. So if you have questions via email, please let me know. But I'm also just going to hang out if there aren't any. Ooh, there, the light's much better now. So send me a either chat on the little chat window, and I'll answer any questions. And anything's fair game. So um, let me know. Remember, it can be about the homework. It can be just about something in class that you want to go over, or maybe something I talked briefly about that you want know a little bit more. I'd be happy to elaborate on. I'll be here until 8 o'clock, so I'll do this for an hour, and then again tomorrow at 2 p.m. So um, I see a couple people are on. If you have questions, let me know. I'm gonna pull up my email on this other computer so I can see if people chat in that way. All right, who's gonna be the first? I can tell you, while I'm waiting for someone to do this, I think one of the cool things about a class like this is just how the large breadth of material, and how I think you can hopefully by the end you'll start to see some cool connections among the various sciences. I know that certainly just in the astronomy and geology portion, um, I've seen huge connections. And It's been really fun to think about that. The challenge, of course, as you've probably already seen, is like you can't go into anything in detail. Cool. All right. We have a question from Eric. It says, can you talk about the radial velocity and where that has come up? Yeah. So radial velocity is just a term for whether something is coming towards you or away from you. It's the radial part is just any direction towards you or away from you. So radial velocity is something moving towards you and or away from you. So in where that's come up in class is, well, I think I only used that term in one context, but we've really used it in two. Um, I also called something the recessional velocity, which is how fast galaxies are going away from us. But that also is often referred to as radial velocity. In fact, in the stellar community, that's actually what we do for stars that are coming away from us or towards us. We use that term. So in galaxies, that could be the same. But where I think it came up was when we were talking about how we measure, how we detect exoplanets around stars. The first method I showed, which was the Doppler method, or I said the radial velocity method, where you're actually watching as the star moves towards you or away from you, and towards you or away from you. And again, you can't physically see the star coming towards you or away from you. What you see is as it comes towards you, its light gets a little bit bluer. And as it comes away from you, its light gets a little bit redder via the Doppler shift. And that radial velocity, the more it shifts towards the blue, the faster it's coming towards you. The more it shifts to the red, the more it's going away from you. And so what you're measuring when you measure a Doppler shift is just the motion towards you or away from you. One caveat we didn't talk about with all of that is that, of course, these orbits, especially in the radial velocity, may not be coming right towards us. The planets may be coming in a kind of a diagonal, and all you measure is actually the motion towards you or away from you in the Doppler shift, and that's the radial velocity. I don't know. I hope that answers your question, Eric. Um, that's the main place it came up, because I don't think I used that term in the galaxy. Yeah, no problem. Others, now that Eric has got us started. Remember, anything's totally fair game. It can be about class. It can be about the homework assignment. Um, it can be about anything else in astronomy. I'll tell you if I don't know anything about it. Yeah, so Maya, I'm a little confused how to determine density and moment of inertia of a planet. Okay, so so is this specifically about the homework? Well, I'll give you the general one, and then if you want to go over like an example, we can do that. So the density of a planet, there were really four densities I wanted to make sure that you knew. So, I want you to know that water is 1 and that ice is a little bit less than 1. That's in grams per cubic centimeter. Rock is 3 grams per cubic centimeter, and iron is, just less than 8 grams per cubic centimeter. And in the context of understanding what planets are made of, or their densities, what I want you to know is there were a couple different things that we talked about in class. So the way you would measure a density, if you had the material, if you had to do it, would be the mass over the volume. But like in the homework, we didn't give you that. But I think one of the things we ask you to do is find the density of one of these planets. And so one of the things that we asked you to think about was, if you remember, I think on the homework assignment specifically, I said that all of the worlds, the Star Wars name worlds or Star Trek name worlds, are terrestrial worlds. They're worlds that you can stand on. And if we look in our solar system, the farther you go away from the sun, the lower the density. And that's a product of that condensation sequence. The fact that when you're close to the sun or a star, you can condense things like iron and rock. And so close to a star, the only worlds you can build things with are iron and rock. And so worlds you can stand on near a star are almost always going to be higher density. Whereas as you go farther away from that star, you can now start to build worlds that are made of rock, iron, and ice. And as you get farther away from the star, there's a lot of ice to build worlds with. And so the worlds that you build really far away from a star, especially the ones you can walk on, have much lower densities closer to water or ice. And so that sequence is one I kind of wanted to have in your brain. That was actually a nice plot that showed that density decreases as a function of distance. So if this question is about the homework, you'll notice that I give you the distance that those worlds are from from the central star. And I hope that you'll see that the one that you don't have a density for is actually the farthest planet. And so I want you to then now make an educated guess on the density based on that information. In terms of moment of inertia, so I hope that answered your question. If not, I'm happy to go into further detail or a more specific aspect. But let me give you the quick moment of inertia. Moment of inertia factor is a measure of how distributed the mass is. So if you had a giant, and for this case, we're going to always assume that planets are perfect spheres, which is mostly true. They're not perfect spheres, but they're pretty close. So a perfect sphere made of all one material, whether that material be rock or iron or water, if it's made of all one material, perfect sphere has filled with one material has a moment of inertia factor of 0.4, okay, no matter what material. That's also true if you took a bunch of rock and iron and water and mixed it all together and mixed it perfectly evenly. So it was homogeneous or homogeneous, like that you had the same amount of rock, iron, and water in every little part of the sphere. It still would be 0.4. Where it gets different is when a world becomes differentiated. That's the term we learned about, where all of the dense material sinks to the center of that world. So let's say you had a world like Earth that has mostly iron and rock. When the Earth differentiated, the iron all sunk to the center, And when it sunk to the center, Earth's moment of inertia factor went down to below zero point 0.4. It's 0.35 or something. So how do you determine that from information that I might give you? Well, let's say that you knew the density of a world was, I don't know, let's say 5 or 6. So I know it's a combination of rock and iron if it has a density of 6. And let's say that I see that the world is, I don't know, has a rocky surface or something. So I don't see it's like a mix of rock and metal. I see a rocky surface. So in that case, I know that the world must have rock on the outside and there must be iron on the inside to bring the density up. And so therefore the moment of inertia must be less than 0.4. Now I'm never going to ask you to calculate, is it 0.35 or 0.32? In those cases, all I care is that it's either 0.4 or less than 0.4. Like that's all I care. And this is actually true of some of the homework questions where you have to give a density, or I'm trying to remember what the other, I could pull up the homework, what the other factor you have to calculate is. In those cases, all I want you to say is, I'm not looking for an exact answer. I'm looking for you to say, this is greater than this or less than this, or less than to equal this. I don't know if that helps you, Maya, but if not, ask me even a more detailed, specific aspect. But that's a long answer for a short question. Find the size of a planet. Oh yeah, right. So that was the other thing that it asked, right, on the homework, was the size. So so how do we find the size of a planet? Well, the only time that we've talked about really size in this class was in the context of geologic activity, and so I think that's where I'm asking it in the homework. And so the one thing that we talked about for worlds that are geologically active is that it seems to be that the larger worlds stay geologically active for a longer amount of time. That's certainly what we see in our own solar system. And we don't have we can't actually tell if any of the exoplanets that we've discovered yet are geologically active. But certainly, and what we mean by geologically active has volcanoes, have, in Earth's case, plate tectonics, some of the stuff we started to talk about today. In the case of like the solar system, Earth is geologically active. There's evidence that Venus is still geologically active. Mars looks to be dead. So it was geologically active, certainly in the past, but isn't anymore. Moon was, but isn't anymore. And so that all is a function of size, we think. So on the homework, when you're looking at, I think I identified 2 worlds that I said were geologically active. And one of them you know the size of, and the other one you don't. And so a good guess for the other world you don't is that, well, it has to be probably at least as big as that world that's geologically active. It could be bigger. There's a tiny possibility that it could be smaller, but the right answer, of course, is that it's either as big as that world, as the world you know the number for, or bigger. And so any number, the way I would answer it was just say bigger than, I can't remember if it's Spock or I don't have it in front of me, but you guys I can look it up if you want me to, but I don't know if that helps. That's the one context we've used size in the class. Certainly size plays a role in density. Bigger worlds have more volume, but we didn't talk about actually computing density. And I wouldn't ask you to do that on an exam, for example. But I would expect that you know that larger worlds stay geologically active for longer. And of course, today, here's the hint for the couple of you who are still on. The big hint is that in today, we talked about not only is geologically active or geological activity important for things like having volcanoes and having plate tectonics, but it's essential to having a magnetic field, right? So I could give you a question on the exam or something where I had um, asked which world is most likely to be geologically, which world is most likely to have a magnetic field, and you would want to find a world that was geologically active, and if you remember, the second thing was rotating quickly. And so I might give you the rotation rates of all the worlds, and I might give you the sizes of all the worlds, and you would want to find a large world that was rotating quickly. And that would be the one most likely to have a magnetic field. So that's like big hint. Not going to say that's going to be on the exam, but I may or may not have used that in the past. Does that help you, Maya? Sweet. And gives you a nice hint for maybe later. I am probably gonna, the TAs and I together, along with Dr. Campbell, we'll put the exam together at the end of the geology block. And the way I really like writing exams is similar to the kind of question that has the table where I make up a bunch of fake worlds. Obviously, I've had you guys do that in class. I've had that on the homework. I think it's a great way of doing an exam where you don't memorize, a bunch of known worlds and known parameters, but instead I want to test that you conceptually understand the concepts. And so I could make up, a bunch of fake planets in a solar system, and I could ask you a bunch of things about them that test your understanding of both the astronomy and the geology that we've learned, just based on their properties. And so that's likely going to be an element of the exam. Other things. Let's see if I have. While I'm waiting for another question, I'm going to see if I have. When I was prepping to bring in the meteorites to class, I think I must have left these in another room. I have another one I could actually show, but don't have it here. I left it in another room. That's too bad. Oh well. I used to keep it on my desk here, but my desk has gotten really messy. So I don't seem to have it here. I'm going to show you a different type of meteorite, but maybe I'll bring that. Make sure I have that tomorrow if someone wants to see one. You can just buy the meteorites online. The one that I actually passed around is actually pretty expensive, but you can buy a relatively inexpensive one. You can buy a little chunk of one for like $20. There are really fancy meteorites, like pieces from Mars or the moon. So like when large impacts hit the moon, some of that material, most of the material stays on the moon, but some of it actually hits the Earth on the really big ones. And the same with Mars, like on really big impacts on Mars, some of that material hits the Earth. And it's actually pretty easy to tell a rock that was on Mars on Earth because it actually has different chemical content. Its specific ratios of types of elements are different than ones we find on Earth, significantly different. And also they can do these cool tricks where they can heat up the rocks and the atmosphere comes out of the rocks, the gas that was trapped in the rock, and it actually matches what exactly the Martian atmosphere is, which is really cool. Anyway, a piece of Mars, if you found one of these meteorites, they're worth like more than like gold or any precious metal. It's pretty amazing. They're pretty spectacular. I worked a lot of the professor when I was a graduate student. The professor where I learned most of the geology from was actually a geologist at the University of Washington, and I actually taught a lab class for one of his geology classes, which is where I learned a lot of the stuff that I've been teaching you guys. and his expertise, he was a geologist, but his expertise was actually on meteorites. So I got to actually go to his lab, and he often had chunks of like Mars and the moon that he was studying, and he would actually, part of how he paid for his research is he would verify these rocks for collectors. So people would find a big chunk of a meteorite, and they'd want to know: is this a piece of Mars? Is this a piece of moon? Is this just from a piece of? Is this a meteorite at all, or is it from an asteroid in the asteroid belt? And so he would take a piece, and he would actually get to keep that piece for his research, and then he would verify it for them. Because if it was a piece of the moon, it was worth a ton of money, and same with Mars. I mean, crazy, like I forget, tens of thousands of dollars for like a gram. It was like crazy. So pretty awesome. But we got to touch a piece of Mars, which was really awesome. So there are some really expensive ones out there that are way above my pay grade. All right, anything else? I'm here until 8. All right, sweet. Check this out. Answering question 4 on the homework. Okay, you're gonna make me have to now pull up the homework. So hold on, I have it on the desktop here. I'm gonna go away for a second, but I think I'm still there, but let me pull it up. I will anticipate that better tomorrow. It's in my. While I'm doing that, let's see. There's one other question. Mai asks, wondering how would you tell if space is uniformly expanding? So this is probably referring to one of the questions on the exam as well. So this is that concept that we did where I drew the picture of Massachusetts. Oh, it's the same question. Sweet. Haha, talking. Yeah, about the same question. Okay, awesome. Great. Well, this has to do, I'm still going to pull up the homework just in case other people have homework questions. There we go. Tufts. All right. Coming up. Word is launching. All right. So this whole question, the question of the uniform expansion, has to do with when I drew that picture on the board of Massachusetts. And I don't know if you guys remember that one. Oh, for some reason, not. Hold on. I'm sorry. I'm going to have to find the copy that. Search. There we go. Much better. Just search for it. Okay. So if you remember when we were talking about Massachusetts, I said that if we were in Medford, and that was like our center point of the universe, like that's where we're observing the universe from. And then I had a drawing of several cities. So let me actually do this for you guys here, and we'll do it a little differently. Let's see. I think I can do this so you can see. So I'm going to make this much easier. Our universe is just a square, so you can see like that, okay? Or that's a four-sided object. And if we start in, I'll try to make it kind of close to where you, analogous to where the way the homework is. So if we're sitting at the star, and there's, let's say, object 1 and object 2, and we can see those, and you can see they're at 2 different distances from each other. The idea was, if you now expanded the universe uniformly, which meant, let's say in this case, we made it all dimensions 2 times bigger. Hopefully you can see that, yeah. So now the square is twice as big on every side. So now you have the star here. Let's see, number 1 is there. Let's see how good my drawing is. So now your universe looks something like this. It's expanded uniformly by 2 times. Okay, the key thing was to think about what happens as you're looking at if you're sitting at the star, that's like our center of the universe, and you look out at points 1 and 2, how far away, A, do they look like they are now, and how fast do they look like they're moving? Okay, so let's say, I'm going to try to use different ones than the homework so that you can then try it yourself. Let's say number 1 is, I don't know, 5 units away, and number 2 is 8 units away. So that's here. We'll make this better. You can see that. Sorry. 1 is 5 units from star away. 5, we'll say miles, and 8. Number 2 is 8 miles away. Okay. So that means when you go to twice as big, and let's say this expansion happens in 1 second, we'll make the math easy. Now, 1, instead of being 5 miles away, everything is expanded uniformly by a factor of 2. So now 1 is 10 miles away, and 2 is 16 miles away. Okay, so you get a picture of how it looks like that. So hopefully that is okay. If not, let me know. Now if you were sitting at star and you were watching 1 and 2 as the universe was expanding, you would have said, okay, wow, 1 was at 5 and it went to 10 in, let's say, a second. So it looked like it was moving at 1. So 1 was moving at 5 miles per second. Okay, 1 was moving at 5 miles per second. But when you were looking at 2 went from 8 to 16 in 1 second. So it looked like it was moving at 8 miles per second. Okay, so just even in a uniformly expanding square or universe, this tells you that these two objects, even though everything was expanding uniformly, these two objects appeared to be moving at different breakthrough that Hubble made when he was, sorry, my lights on my computer went out. When he was looking at the expanding universe, when he was looking at distant galaxies, he found that the more distant galaxies were moving faster away. Now, when I was in college and I first learned this, because I didn't learn this till I was in college, I had a professor who was kind of pompous and was like, hey, this is obvious, like, or I don't know, trivial, that like if you have faster things farther away, we must be in an expanding universe. And I looked at him like he was crazy, because for me, like, this was not a simple concept. I was not like, oh yeah, that's obvious. I had to really do drawings like this. And so I don't know, maybe just doing this, you're like, oh yeah, I get that. But if you're not, I would draw a bunch of examples of this, and actually draw more than just 2 examples. In the homework, we ask you to do 2 examples of this, but I would do many more than 2, because what I think you have to start wrapping your brain around is that things farther away indeed actually are moving faster in something that's expanding uniformly. And to me, that's still just barely obvious. And I've done this a lot. And so I think you have to really draw the picture and actually see that for yourself. It's why I did the Massachusetts example in class. And it's kind of why we want you to do that in the homework, is to really kind of wrap your brain around the fact that it is actually true that if you uniformly expand any shape you want, right, things farther away will look like they're moving away faster. You could even do this on a balloon. I mean, don't do that for homework because that's a pain in the ass. But I don't know. Hopefully that helps those of you who had that question. Oh, good question, Lauren. So Lauren asks, you guys can probably all see it, but I guess I'm going to repeat for people who are just watching. Sounds like the universe has edges to it, and it's not something to it if it's something that can expand. So that's actually probably not true, which is this. We're going to get into kind of confusing land, but actually fun confusing land. So for purpose of like understanding this, we like draw things with edges, or I draw like the shape of Massachusetts. But if this were even like infinite, which is like crazy to think about, if you know if that's if even if this were infinite, this still would actually be true. And one possibility is that the universe actually is infinite. It's not something we can actually test. I mean, what is true is that where there is an edge is our ability to observe, right? So we can only observe as far away as it takes light to travel, right? Because the universe has only been around for 13.8 billion years, and it takes time for the light to travel across those vast distances. And so we do have an edge of that we can observe. And so in that case, maybe that helps you wrap your brain around this. But one possibility is actually that the universe itself is infinite, that there is no edge to it. Like one question that some students often ask when I teach this is like, okay, well, if the universe is like a balloon expanding, 'cause that's another kind of good example, but it's not. In that, one question people ask is the balloon expanding into something, right? Like, what's it expanding into? And the thing is that the universe is all there is, right? Like, it is all of space. It's not like a balloon expanding into a room. The universe is the universe. It's like all that there is. And so when we're talking about space expanding, it's literally the space between things expanding. So it'd be like if you were sitting in this room next to me and all of a sudden the room just got bigger, right? Like the space between us just got bigger. And that actually is the concept of space. Because remember, even at this point in the universe, it's expanding faster than the speed of light. Now we know that nothing can travel through space faster than the speed of light, but it turns out the universe can expand faster than the speed of light. Woo, super crazy. So a lot of people, I had a colleague when I was a professor at BU who would say, who actually studied this stuff and said, people would say like, well, what does the universe expand into? And he would say, the future, which I thought was an awesome answer, because of course it is the future, right? Like the more we expand, the more you can actually see both into the future and the past. Lauren's asked a couple of questions. Is it because of curved space-time? The curved space-time has more to do with probably some of the differences you might have between the distance and the time. So the fact that like the universe could be could take longer for light to travel through a curved space, but it actually turns out but there's actually all the evidence points to space, except for around a gravitational object, being pretty Euclidean, like pretty straight. Like shortest distance between 2 points in space is a straight line, except for around a massive object like a star or a galaxy or a black hole or something. And we've talked about the curved space-time in those cases. But there was actually, when I was first learning this stuff, it was crazy. Like people thought that actually space itself might be all curved, like you were walking on a globe, right? We actually all know a curved space-time, right? We sit on a globe and we like think we're all nice and flat and level, and yet we're like on the edge of a curve, right? And there's lots of crazy crap that happens on a globe, right? Like you have parallel lines that meet, right? Like the lines of longitude are parallel at the equator, right? And they're parallel the whole way, but guess what? They meet. And you learn in geometry, like that ain't possible, but on a curved space, it is. So there's lots of like weird geometry that happens. And actually that was like one possibility for the universe, is that it followed this curved geometry. It all evidence points that that's luckily not the case, or else it would make things really complicated. Sorry, I need to get back to Lauren's questions because she has some really good ones. Faster than light. Yeah, so the universe is actually, it's been accelerating so much for the last many billions of years that it's actually the space between two objects is actually the space between us and the most distant objects are actually moving faster than the speed of light at this point. So at some point, things will actually be moving so fast that we won't ever obviously catch up to them, right? Like if it takes time for that light to come to us and it's accelerating away from us faster than the speed of light, like we'll never get that information, um, which makes sense. So that's pretty crazy. And what's Warren's other thing? There's a philosophy of physics program at BU. Yeah, they're certainly in the philosophy program. They do a lot of philosophy of science. There's also like history and history of science. Do they do a lot with that kind of thing? There's some amount of that. It's also a lot more about like how scientists come up with theoretical ideas and thought. So some of it has to do with kind of bigger concepts of the cosmos and how that's kind of a theme throughout kind of the history of science and that philosophical idea. But there's not as much detail about the specific cosmology. This whole topic is called cosmology, or the origins. But there are entire courses like at BU, even some at the like non-majors level. And actually, there's like great professor at Tufts who teaches like one of his expertises is in extragalactic astronomy. I don't know. I know he teaches like an intro survey course of astronomy, but I don't know if he teaches one specifically about cosmology. But he'd be like also another great guy to talk to about this stuff. Lauren, what does that mean that the universe is destined to get cold and dark? Yes, it is very true. So the universe is destined to be cold and dark and distant and lonely. It's actually kind of depressing. I'm debating like what we're going to do on the last day that you have with me. In the syllabus, it says we're going to do kind of the ends of everything. And Lauren's question just now asks, does that mean the universe is kind of destined to finally just everything expands apart from each other? You'll get some things colliding still with each other for like the next probably billions, tens of billions of years, but eventually things will get so far apart that you won't be able to see any other galaxies, and it will just be dark and cold, and it's like, yeah, I find it like a little depressing, but it is the reality. I mean, eventually even all the stars, in our own galaxy will burn out. Even the little M dwarfs that last 1 trillion years, at some point they'll run out. They'll run out of gas to stop forming them, and things will go pretty dark and cold. I got an email. Oh, it's from Dr. Campbell. Oh, so what happens to the information caught in the event horizon of the black hole? Well, once it goes in the black hole, once it goes through let me back up for the people who don't remember or don't know what event horizon is. So on a black hole, we briefly talked about this. Black hole is literally a single point in space. Like it has mass, but no size. So it has infinite density. But it has a sphere around it. That's kind of its sphere of influence. That is the point of no return. And it's actually mathematically defined as the point at which even light, which is the fastest thing we know in the universe, even light cannot escape that radius. And that's called the event horizon, or the Schwarzschild radius. And so once something goes in there, it's gone. It's never coming back. What happens to it? Well, it really probably depends what it is. If it's just like a star, say, falls into a black hole, the star is consumed. It adds to the mass of the black hole. It actually makes that radius, that event horizon, get bigger. In terms of the information, don't know specifically what you mean by it, but like its history, its all of that, it's at least gone to us. Now, it's at least gone to us. Now the question is, what we don't know is is it retained elsewhere? So some people think a black hole might open to another opening in another universe or something, that like when you fold space like that in on itself, that it folds into another dimension beyond time, that it might actually be fold into like another universe. We have absolutely no evidence of that, but these are the types of things that people think about to try to understand this. All we know now is that it basically disappears. Now, there are a couple of kind of caveats to that, and I think a couple cool ones while we're talking about black holes. You can actually have particles that kind of split into two other particles. Think of it like a proton and electron, but it's actually even smaller pieces than that. And those can actually come speeding towards a black hole. And if they actually break into their two pieces, so say they break into, let's just use proton and electron as an example. You have an atom, it breaks into a proton and electron. You can imagine a scenario where this thing's speeding towards the black hole and it's about to go on the event horizon, but it splits into these two things, and the electron goes into the event horizon and the proton goes zooming away at really fast speeds. It turns out that two really cool things happen. One, that proton actually may retain kind of some information from the electron, right? It had that piece of the electron there. And so observing that proton tells you, and I'm using proton kind of in now quotes, since that's the type of particle most people have heard of, it had a pair that it no longer has. And so it actually retains that information, which is interesting. The other thing is in coming towards the event horizon, that particle was accelerated, and that actually took gravitational energy away from the black hole, and some of that energy is retained in the pair that it the piece of the pair that it swallows. The other piece leaves, all right, and it carries with it some of that gravitational energy of the black hole. That actually makes the black hole actually get slightly smaller. And we actually call that process Hawking radiation. Stephen Hawking came up with that idea. And we actually think this makes black holes over time shrink very, very slowly, super slowly, but they actually lose mass. They transfer their gravitational, their mass, which is turned into gravitational energy, is actually absorbed by some of these particles that leave, that actually don't get sucked in and leave. And then over very long amount of time, billions of years, black holes can shrink because of this, which is a really, I don't know, it's kind of a cool concept that these even great monsters in nature can be essentially vanquished by the tiniest particles in nature. So I think that's a neat concept. Great questions, Lauren. Are you the one in class who was like, oh, did we talk about black holes today? Cool. Keep going. I've got 15 more minutes. Happy to do anything more. And it can be class, it can be cool questions about black holes or exoplanets or small stars or anything else. Oh, so Lauren says, I'm stuck on the question about someone else raised about the average mass of the universe being potentially infinite and the implications this might have for the expansion of the universe. Yeah, I mean, I think I'm stuck on this philosophically as well. For sure, I'm stuck on this philosophically because there are a couple ways of thinking of it. If you just added up all of the things in the universe with mass, right, and or the density of things, right, in the universe, and you added up a bunch of densities of things and average them, of course, like the black holes have infinite densities, and as soon as you add infinity to anything, it becomes infinity. Okay, so but another way of thinking about this, which is how I wrapped my brain around it after it was asked in class, was thinking about it like, rather than thinking of it as adding up a bunch of densities, let's just add up a bunch of mass, right? So, even if the black hole itself is a single point in space, it's really still just mass, right? Like, let's take away the point that it has no size. Let's just take now that like it's adding mass to the universe. So if that size, got folded together, and that's a whole other philosophical question we can have. But it itself is just a single piece of mass in the universe, right? And in cases of like stellar mass black holes, that's just they're about the mass of the sun, right? So it's not a ton of mass. Even a black hole at the center of a galaxy, our own Get one is like 4 million times the mass of this, 4 million suns in mass. So in terms of their implications for like the expansion of the universe, black holes probably aren't a huge amount of mass, right? They still make up what we would call normal matter, right? Which, if you remember that pie chart from one of the first days that we had of the semester, the normal matter in the universe is still only like a few percent of the total kind of energy mass of the universe, right? Most of it is either in dark energy, which is what's responsible for the expansion of the universe, and the acceleration of the universe, really, and this dark matter, which we didn't talk a lot about, but is matter that for some reason we think is out there because we see indications that there's stronger gravity than there should be, given like all the stars and gas and dust that we see. The best example, which I think I briefly said in class, was when galaxies rotate. They rotate faster when they have more mass, just because in order to like sustain the orbits of the stars, they have to rotate faster. And most galaxies rotate much, 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 much faster than they should be, given like all the stars and gas and dust and everything we can measure. And it actually is like a lot. It's like missing a ton. So in our own galaxy, if you add up all the stars and the dust and the gas, and you're like super conservative about it, and you take into account, like all the uncertainties and things we think we might not see, like we're still missing like 90% of the matter in our galaxy based on how fast it's rotating. And so it's like, that's crazy. Like that 90% is missing, and we actually have no idea what it is. For a long time, people thought it might be like little exoplanets floating out in space, and we thought it might be like like these failed stars that we didn't talk about called brown dwarfs. So stars that are like, well, they're not quite stars, they're like almost stars, but they don't get hot enough to start fusing hydrogen. So they're like basically almost the mass and size of small stars, but they don't quite get hot enough in their cores to start fusing hydrogen. And if there are a lot of those floating, and then, so they're not bright almost at all. They get a little hot from expansion, and then they kind of cool on forever. So if you had a lot of those floating around the galaxy, that could make up for it. But in the late 90s and early 2000s, there was like a really cool experiment where they did this targeted search for them, and they found some of them. They were called MACHOs, massive compact halo objects. Funny acronym. But basically they found some of them, but there wasn't anywhere enough to make up for even like a few percent of the dark matter. And so the best candidate now is something that people call WIMPs. It was either WIMPs or MACHOs. And the WIMPs appear to have one. They're called weak interacting massive particles. So some kind of particle that's very massive, but is very weakly interacting, which means it doesn't feel much force or collide with other particles very well. And that's how we detect other particles. When they collide with each other, they might create light, or they might bend, create some kind of energy or something like that. And most particles, via electromagnetic forces or other forces, interact with each other. And it's very likely that the dark matter particles just don't interact with each other. And so people are off looking for them. It's one of the things that some of these like big super colliders are looking for. No one's found anything yet, but when they do, they'll win the Nobel Prize for sure. Like that's a guaranteed Nobel Prize win, whoever finds what dark matter is. But it makes up a lot of mass. For a long time, I didn't like it. I wanted like dark matter to go away, and I wanted it to be that just maybe like physics was understand. But it turns out now there's like lots of different lines of evidence that dark matter is real, which is not as satisfying because it means it's got to be this little particle that we don't know about. So it's gone from like cool to like not super satisfying, but still interesting, and still humbling that like we only know like the stuff that we talked about in astronomy is still like this tiny percentage of like what's out there and what we know. So astronomers won't be in business for a long time. Yeah, totally. I mean, you can keep going on a roll, Lauren, and I'll interrupt if someone has another homework question. This is what like normal office hours are like. That's what I find. I always had people who come in and like want to just like shoot the shit about cool astronomy stuff, and then other people who were like, I got to get problem 4 done. So we do some of both. Yeah. So this is the so the entanglement stuff that Lauren you're talking about. That is actually potentially another way that black holes could transfer information, but the entanglement issue is that how can I say this nicely? Particle in very small scale physics, in like quantum physics, particles retain certain properties, and like pairs of particles often have like matching properties. So if one is like spin up, like you may have learned that in chemistry class in high school or something, that you can have electrons that spin up and down. And there are lots of properties like that. There's lots of like rotational and spin states. When you get into the like hairy details of the physics of particles, and as Lauren just said, yeah, it's something you definitely learn in a theoretical, in like a quantum physics class that like you would take as a physics major, or chemistry majors have to take it. Although they call it PChem, or physical chemistry, but they would have to learn about this too. It's actually like really cool stuff. It's what like sets the periodic table the way it's why it looks the way it does, is like all these interactions. But the cool entanglement part is that that these pairs, like if you kind of pairs of particles that kind of have matching things, one is like always up and the other one's down. And so one of the ideas is if you could find a way to like separate these particles and then change this one to up, this one would like go to down. And if you move this one to down, this one would go to up, right? Like that's like kind of the layperson example, right? And so if you then did that over vast distances, the idea is that like potentially you might be able to, that this one just knows that when this one goes down, this one has to go up, and this one goes up, this one goes down. Now there may be some piece of that we don't understand. There may be some force or some communication that is between those. For example, like light communicates between all of the electromagnetic interactions. That's actually how you have the bond between electricity and magnetism is actually light. That's why light is often referred to as electromagnetic radiation. And so that wasn't known for a long time. People thought just like magnets and electricity was kind of this magic crap. But it turns out it's all interacted through light, which is like really, really neat, right? Like when electrons actually get bent around magnetic fields, they actually like spit off light. And so it could be that like even in the quantum realm, we're missing some like other interaction that actually may have a finite velocity like the speed of light. And that even when you flip this one here, this one flips, but it takes some time for that communication to happen. But the basic idea is that you could take the two components of this pair, move them apart, kind of, change this one, and in doing so, it changes this one. That hasn't been successfully done yet. at these like vast distances. You can do it like in the lab, and it actually works. It's just pretty cool. But they haven't done it at like the moon or somewhere where like you were appreciably away, where you could measure if it's faster than the speed of light, or if it even works on those distances. But you can do it in the lab, and it's really neat. I mean, there's a lot of cool, weird things in quantum physics. I think I mentioned this in class, like when we talked about the radioactive stuff, like most things at the small level or minute or quantum level in physics and chemistry operate statistically. So there's like a statistical chance that something's going to happen. In fact, even when we were looking at those tubes in the classroom where I had the gas in the tubes, and I was electrifying them, what you're actually seeing, and if we had more time, I would have described this. What you're actually seeing is you're seeing electrons that are actually blown off their atoms. So in the case of neon, you put so much electricity into a neon atom that you blow the electrons off. And as the electrons want to come back to the neon atoms, when they do that, because of the electric charge, the neon atom is positively charged, the ion is positively charged, and then the electron is negatively charged. It wants to stick to it. When it sticks back to it, it actually emits light. And that the light actually happens at these very discrete energy levels. And that's why you saw all those different lines in the neon, was the electron actually coming down to all those energy levels. And that's pretty cool. Oh, I vaguely remember the part of the big deal about entanglement was that the active observation is to determine the spin instead of the spin. Yeah, so that is, I mean, I was going to say that in where I was kind of going with this, the statistical things, although I'm kind of ranting, but the statistics part is that like everything kind of statistically happens, but one of the kind of mantras in quantum physics is that like when you like view something, when you actually observe it, you are observing it, you are setting its state, that before you actually make the observation, it is in what's called a state of quantum flux, where it could be statistically in one of a number of different states. Now, some states might be much more likely than others. They might be 100 times more likely, or 10 times more likely, or 2 times more likely. But that actual thing that you're observing, whether it be the spin of a particle, as you say, or the actually energy level that you observe the electrons jumping from, like whether you're observing having them jump from different energy levels in the electron energy diagram. I don't know if you remember that from a chemistry class, but that you don't actually, that electron isn't in any of those states until you actually observe it. And that's the like whack crazy thing about quantum mechanics, that like is that nothing is kind of set. It's in the state of quantum flux until it's observed. But when it's observed, then your if it's in one of these like pair, like you were talking about in the entangled particle things, you set the other particles. So if you observe a particle in one state, then it immediately changes the other particles, and it can actually be more than one. If there's like many particles entangled, they all set to their relative statistical proportions. Oh, now you're talking about Heisenberg. You can know the velocity of something, you can't know the precise location or both. Yeah. So that's called the Heisenberg uncertainty principle, and that's talking about this is all stuff at the really quantum level. Like obviously, you can determine my velocity, like you can see where I am, and you can see how fast I'm moving. Okay, so none of this is for very small or very large macroscopic things, but it is true like at the microscopic level or at the quantum level. For example, an electron orbiting its atom, and they don't orbit in nice orbits like a planet orbits a star. They actually kind of in a cloud, and at any one moment you can either know where it is or how fast it's moving, but you can't know both to within some like uncertainty factor. And that actually just is a statistical property, which is pretty cool. It turns out that is equivalent to energy and time So you can actually change around the Heisenberg uncertainty principle to be that you can't know the energy of something and the time it takes for it to like do its to make its energy transition, and that's actually directly important to things like radioactive decay, because that's releasing energy in a certain amount of time. And that's, like I said, it was a statistical property, where sometimes, like you don't know how much energy or how long it's going to take for a single atom to do its decay. On average, when you have a large sample of them, the statistical abundance of how much is going to decay over a certain amount of time. And it's actually also super relevant to the spectral lines. Right. So the spectral lines are whether you have them go from a certain state to a certain state is governed by like how long it takes to go in those states, and the certain different lines that you see are different energies, and so which ones you see for a specific element, you can either know how long it's going to take to jump or how much energy it's going to take in certain detail. But in that case, in the tube of the neon, we were looking at like, I don't know, many moles of neon, and so there's a bazillion particles in there, 10s to the 23 particles, and so there's statistically we know exactly where all the lines are going to be. But if you were tracing a single electron, you wouldn't be able to know that information. You wouldn't be able to note both of those pieces of information, which is pretty cool. Yeah, and that's why we flipped coins. We flipped coins to show that it was this. I wanted you to see two things. I wanted you to see that it is just a statistical process, and that statistical process in a class even as the size of the Big Bang humankind class, like that you actually get about the right answer by doing it quickly, even though there were people who like could flip heads a million times. Most people, or the aggregate of the class, followed like the nice exponential fall. And to show you that, like, if you have a big collection of potassium, radioactive potassium, like we know how long it's going to take for like half of that potassium to turn into argon. All right, it's just after 8. Any last question, Lauren? You are totally welcome. You're welcome to ask lots more random questions in class, or email me, or in a different office hour. So I guess I will talk to you guys all tomorrow, or see you in class on Thursday, and let me know by email if you have any more questions or if you have any other questions. All right, good night.